So what we're going to look at today is we're going to look at several steps you go through to figure out how to solve problems. So when you're approaching a problem and you're asked for an antiderivative, the first thing that you want to do is answer the following question. So let's say, do these steps. First thing we're going to do, look, do you see anything that can be easily rewritten? If so, do it. So these include things like exponents, so the antiderivative of the square root of x dx becomes the antiderivative of x to the 1/2 dx. The antiderivative of sine squared of x dx becomes the antiderivative of the sine of x squared. These ones look really similar to the ones that we had for derivatives. So we got the antiderivative of 1 over x squared dx is the antiderivative of x to the -2 dx. There's just one that you should not rewrite, and that's the one that doesn't fit in the power rule. That's 1 over x dx, because if we do that as the antiderivative of x to the -1 dx, then we'll get division by 0, leave 1 over x as is, because that's just the one where we have to remember that the antiderivative of 1 over x dx just equals the natural log of x plus c. Well, those are the ones rewriting that we had from when we were working with derivatives. There are a couple more rewrites that are more important for antiderivatives. So functions that are easy to multiply should be so if we have something like the antiderivative of x squared times x to the 3rd dx, that should be rewritten as the antiderivative of x to the 5th dx. That makes that possible to take the antiderivative. What we also saw in earlier lessons, if we have something like x plus 1 squared, we should rewrite that by expanding that so that we have something that we can use the power rule on. Likewise, we also saw in antiderivatives 2 rational expressions. Those are those fractions with a single term in the denominator. So for example, the antiderivative of x squared plus 6 over 3x dx is something we should rewrite by breaking it up. And these cancel out. Okay, so any of these things that we've done, our goal is to get to a point where we have only functions that we have exactly the formula for, and they're separated only by addition or subtraction. So if that happens, and that's what was happening in Antiderivatives 2, that's where we're going to look for our second step here. We want to say, do we have only functions that you have exactly the formula for, and are those separated only by addition and subtraction? So that means we shouldn't have two functions multiplied together, shouldn't have two functions divided by each other, just addition and subtraction in between them. If we have that, we can take the derivative, or excuse me, the antiderivative, if not, we'll need U substitution. So for example, if we had this one up here where we had the antiderivative of 1/3 x plus 2 times 1 over x dx, the 1/3 is along for the ride. This is x to the first. We increase the exponent by 1 and divide by the new exponent. Here the 2 is along for the ride. The antiderivative of 1 over x is the natural log of x plus c, or x squared over 6 plus 2 natural log of x plus c. And when we take the derivative, that's 2x over 6 plus 2 times 1 over x plus c, which is going to be what we started off with. So, if we haven't managed to get our antiderivative done using these steps, that means that we're going to have to use U substitution. So the next piece that we're going to go into is we're going to try to figure out how to determine what our U should be. So our third step determine what to use for U in U substitution. And the way that we do that is we look for box functions. So remember, in this case, that's something to the nth power, sine, cosine, tangent, etc. of something, e to the something, or 1 over something. One of the things that's going to be very important is that the derivative of U must cancel any variables that are outside the box. If there are no variables outside the box, the function in the box, that's U, must be in the following form. U equals Cx plus K, where C and K are both constants. and they may be 0. And the reason it has to be in this form is to avoid introducing another variable. You see, what happens when we're doing U substitution is that, remember, we have to end up with that du in there at the end. And the only variable that we're allowed to have if we have a du is a u. So when we were doing problems in Antiderivatives 3, we saw things like this, where when we substituted u in, the other variables that were there canceled out. When we're choosing our u, we have to make sure this happens, because we can't take the antiderivative until we just have u's and just have a du. So let's do a bunch of examples of this. Start off with the antiderivative of x times x squared plus 10 to the 16th dx. Now we can't expand this out very easily because of that x to the 16th. So now let's look for u substitution. So here we have powers. So this would be a good candidate for our box. And when we look at this, the derivative of x squared is going to have an x in it, so these will cancel out nicely. So let's let u equal x squared plus 10. du dx equals 2x. du over 2x equals dx, so we'll go ahead and substitute that in there. Those x's cancel out. This 2 in the denominator is 1/2. So we increase the exponent by 1, divide by the new exponent, add plus c. We've got u to the 17th over 34 plus c. Oops, that's not quite done yet. We started with x, we got to put our x back in, so it's going to be x squared plus 10 to the 17th over 34 plus c. When we check it, we have 1/34 times 17 x squared plus 10 to the 16th times the derivative of x squared plus 10. 2 times 17 is 34, that cancels out. We've got x times x squared plus 10 to the 16th, which is what we started off with. Now let's look at one where we could have multiple options as to what our u would be. So let's do the antiderivative of the sine squared 5x times the cosine of 5x, that's dx. First things first, anytime we see this, we're going to rewrite it. Now, when we're looking here, we see several box functions. There's a cosine, there's a sine, and there's a power. When we have a choice, we generally want to draw the biggest box that we can. Because basically, if we do just 5x right here, that's not going to really cancel out any of these sines and cosines. Whereas if we do the box here, inside the squared, the derivative of the sine of something is the cosine of something, and that seems fairly promising for canceling this out. So I'm going to make a little note. Generally, we want to draw the biggest box when we have a choice. So let's let u equal the sine of 5x. du dx. So the derivative of sine is cosine of 5x. Derivative of 5x is 5. So du over 5 cosine 5x equals the derivative of x. Put that back in there. So we've got the antiderivative of u squared cosine 5x times du over 5 cosine 5x. Now these 5x's, cosine 5x, cancel out. This is a 1/5, so we have 1/5 antiderivative of u squared du. That's going to give us 1/5. Increase the exponent by 1, divide by 3 plus c. That's going to be 1/15. This u was sine of 5x, so it's sine of 5x cubed plus c. When we take the derivative, we bring down the 3 times the derivative of the inside times the derivative of the inside still. Well, that was 1/15, 1/15. 3 times 5 is 15 divided by 15. Let's see, this is squared. We get the sine squared of 5x times the cosine of 5x, which is exactly what we should have. Now let's look at an example that's similar, but a little trickier. So let's say we want to find the antiderivative of the secant squared of 3x dx. So we're automatically going to rewrite this secant of 3x squared dx. But the problem is that even though we want to do a box function right here, if we do that, when we take the derivative of secant, we're going to get secant 3x, tangent 3x, times that piece in the chain rule. And what's going to happen is we're going to have more variables that get introduced here and don't have anything to cancel out with. So I'll just do that sort of as a quick little example on the side of what won't work. So the derivative of u with respect to x is secant 3x times the tangent of 3x times 3. So we've got du over secant 3x tangent 3x times 3 equals dx. And then when we put it in, we have the integral of u squared times du over the secant of 3x tangent of 3x times 3. And this isn't going to work because of these x's. So what we're going to try instead is we're going to try, okay, well there's only one other box function that I see right here. So I'm going to let u equal 3x. du dx equals 3. du over 3 equals dx. And when I come over here, I've got the antiderivative of the secant of u squared du over 3. And now the really key part here is that you really have to have your rules memorized, because the antiderivative of secant squared u is tangent of u. That 1/3 is along for the ride, plus c. You just have to remember that, and you have to have it sort of on the tip of your tongue, mentally speaking, so that you see this and you know that you can turn into this, because otherwise you get stuck right here. So let's put that u back. We've got 1/3 tangent of 3x plus c. And when we do that derivative, tangent becomes secant squared multiply by the derivative of what's in the box. And that's what we started off with. Now let's look at one that uses our new box function. Now, we saw that we could split up sometimes these rational expressions. However, in order to do that, we had to have a single term in the denominator. And here we don't, so we can't split it up. We have to look at something else that we can do with it. One of the things to remember here, 1 over box is now a box function. And there are a couple of other tips that I'm just going to sort of write out on the side here. When we have two functions divided by each other, the denominator is generally u. In order for this to work, this exponent needs to be 1 bigger than this exponent, however. So the exponent in the denominator needs to be 1 more than the exponent in the numerator. And the reason that we have the denominator being u typically instead of the numerator is something that I'm going to put in as soon as we have a little more worked out up here. So I see that this exponent is 1 less than this one, so I'm going to make this be my u. And this actually shows me why it is that typically u is the denominator, and we're going to cancel out the numerator. Because whatever we have here as the derivative of u, when we manipulate this to get dx by itself, it ends up in the denominator. And so it's very hard for us to cancel this out, because these are both in the denominator and they don't cancel. But we can cancel what's in the numerator fairly easily. So the derivative of u ends up in the numerator, or in the denominator. This is true except for the square root of x. Incidentally, we'll get to an example with that in a bit. Making it easy to cancel variables in the numerator, but hard to cancel in the denominator. So when we come back up here, this is going to be the antiderivative of 6x squared over u times du over 12x squared, so those variables cancel out really nicely. 6 divided by 12 is 1/2. Don't know what that multiplication is doing there. Antiderivative of 1 over u du. This just has to be memorized. It's the natural log of u plus c, which is to say 1/2 natural log of 4x cubed plus 7 plus c. And there we are. Let's make sure to do our check steps. So the derivative of 1/2 natural log of 4x cubed plus 7 plus c. The 1/2 is along for the ride. This derivative is 1 over whatever's in the box times the derivative of what's up here. This and this are going to give me 6. So I've got 6x squared over 4x cubed plus 7, which is what we started off with. This knowledge about how to choose u is particularly useful for something like this, the antiderivative of sine x over cosine x dx, because sine and cosine have sort of that circular pattern in terms of the derivative, so it's really unclear which one we should let be u, except that we know that when we take the derivative of u, it's going to be really easy to cancel what's in the top, but not easy to cancel what's in the denominator. So we should let whatever's in the denominator be u. So du dx, so we're doing the derivative, so that's cosine to negative sine. When we get dx by itself, we'll get that there. Now we're going to go ahead and substitute that in. So we have the antiderivative of the sine of x. Cosine of x was our u. And now we've got du over negative sine of x. Those cancel out. We've got negative 1 times the antiderivative of 1 over u du. That's natural log, so we have negative 1 times the natural log of u plus c. Negative 1 times the natural log of the cosine of x, that's what u was, plus c. When we check our work, that negative's along for the ride. The derivative of natural log is 1 over whatever's in the box times the derivative of what's in the box. So the derivative of cosine is negative sine of x. Negative times negative is a positive. We have sine of x over cosine of x, which is what we started off with. Let's look now at one of the few instances where this is not the case. Let's say we have the antiderivative of sine of the square root of x over the square root of x. So if we let u be the square root of x here, that's not going to cancel out with that sine of the square root of x. And we can't just cancel out the square root of x because it's inside that sine. So we'll look for our other box function. We know that sine is also a box function, so let's try that. Although really before we do this, we really should rewrite that. So our box function's right here. U equals x to the 1/2 power. Du dx is 1/2 x to the negative 1/2 power. So it's 1 over 2 root x. Now to get dx by itself, we're going to do this multiply by dx again. But notice here this is division. So to get dx by itself, we're going to multiply by 2 root x. And du times 2 root x equals dx. So because of this property, where this turns into having a negative exponent with the derivative, now this is going to cancel really easily with this. So we've got the antiderivative of sine of u, and I'll put this back in the square root form again so we can see that it cancels over here, times 2 root x du. Those root x's cancel. That 2 is along for the ride, so we've got 2 times the sine of u du. Now When we're doing this antiderivative, we're going the other way, so sine goes to negative cosine. So we've got 2 times negative cosine of u plus c. Negative 2 cosine, let's put u back, that's the square root of x, plus c. When we do our derivative to check, I'll do that rewrite step first. The negative 2 is along for the ride. The derivative of negative cosine, goes back this way. So it's going to be negative sine x to the 1/2 times the derivative of x to the 1/2, which is 1/2 x to the negative 1/2. So a negative times a negative is a positive. The 2 and the 1/2 cancel out. And we've got sine root x over root x, which is once again what we started off with. The very last thing that we have is a check for understanding problem, and then we're all done. So let's do the antiderivative of 2x cubed over 6x to the 4th plus 1 cubed dx. Try that one on your own, or restart the video when you're ready. Pause the video now. So in terms of our box functions, there's one here, but there's only x in it. There's one here, but there's only x in it. So our best bet is this one, because that's the largest box that we can draw. So let's start off by letting u be that, meaning the derivative of u with respect to x is 24x cubed so let's substitute that in. This is good because this x cubed and this x cubed will cancel out. Okay, so those go away. 2 divided by 24 is 1/12. So now we've got 1 over u to the 3rd du. Now, looking at this u to the 3rd, remember, the natural log is the antiderivative of 1 over u to the 1st power, not u to the 3rd. If we have this with an exponent there, we can rewrite this like this and just take it like normal. We're going to add 1 to the exponent, divide by the new exponent, plus c. So this is negative 1 over 24 times 1 over u squared plus c. Let's put in u. So this is negative 1 over 24, 6x to the 4th plus 1 cubed plus c. I've just done some very complicated stuff, so let's make sure to take the derivative to check that. So this is negative 1/24. All this is 6x to the 4th plus 1 cubed plus, that's the negative 3 now, because that was formerly in the denominator. Oops, excuse me, this should be squared, because I've got that 2 right there, so it should be negative 2. This is always a good thing for checking your work, to make sure you catch little errors like that. So we have negative 1/24. We bring down that negative 2, subtract 1 from that exponent, and the derivative of c just goes away. So negative times negative is a positive. 2 divided by 24 is 1/12. And then as I'm going along here, I notice that I forgot to put in my chain rule. I've got to do the derivative of this over here. 4 times 6 is 24, x to the third. So what I have is this is times 6x to the fourth plus 1 to the negative third power times 24x to the third. So this 24 divided by 12 is going to give me 2x to the third. And then this is all in the denominator at 6x to the fourth plus 1 cubed, which once again is what I started off with up there.